I had to change the title a little bit. I was corrected in my English. So it's Tales of 4000 and Some Nights. First of all, good morning, and thanks a lot to ESO for organizing the meeting, and even more so for conducting the service in the first place. Yeah, 4,547 nights. It's almost exactly 13 years. So we got our first observations on January 29th in 2010, conveniently enough starting with tile D001. And on 27th of January this year, ESO took the last data set for our survey. It was on tile E925. So it was a long journey, and it is, in fact, a very large survey as well. At some point or another, there were more than 100 people involved in VVV or VVVX, and some of them you see here. Some of them are actually at the meeting and also were in our 11th VVV meeting last week in Italy. Unfortunately, not everyone could make it. After 13 years, it's probably not really necessary to explain where the name comes from, but since that picture is the closest I've ever come to seeing the telescope, please bear with me. So yeah, survey was conducted at the Vista telescope until this year. It is, in fact, a variable survey. That's some of the data taken from tile in the bulge by one of our students. He is studying our lyrae, and it was Philippe Gran, and this was our original survey area in the bulge, and the southern galactic disk was in total 348 fields. And after the first 6 years, it became clear that there would be more time available, and it was decided we are going to submit another proposal to add to the survey area, and that's where the X comes from. The red one is the original VVV, and we added some fields on the higher bulge to make the field more symmetric to the galactic center, but then it was also decided we are adding we are adding fields in the lower bulge to include Sagittarius Dwarf, and to combine our survey with the UKITS galactic plane survey, we extended the galactic plane area to plus 20 degrees in longitude and went all the way to 230 degrees. Originally, the disk area only covered plus minus 2 degrees, so there was a gap to the hemisphere survey, which was somewhat inconvenient, and it was also decided to add 332 fields in to the lower disk and upper disk to, at least in part, connect to the hemisphere, so to the VHS survey. Yeah. Okay. You probably also have seen those pictures. That's the advantage if you give the first talk. You can include them. So this is from the first run of surveys. This is us. VVV was one of the areas that was not covered as well by the VHS because it's a large area, and it was a bit easier to exclude this. Same for Viking, I think, and the Magellanic Cloud surveys. Unfortunately, VHS and VVV have their fields aligned for us in longitude and latitude because the galactic survey, and VHS does it in round deck. So our fields are slanted against each other. So there were gaps, but with the VVVX, we are now partly overlapping, so which is comes in very handy. The science goals for both surveys are pretty similar. As the name says, we are mostly variability survey, looking for variables like our lyraes, Cepheids. We also look for rare variable sources, and I think Dante will give a talk on that later this week. We have a small group working on microlensing events, monitoring variability near the galactic center, one of the main topics is also searching for new missing globular clusters in the Milky Way, open clusters, and I think Valentin has searched for clusters in his talk later this week as well. We have a group working on high proper motion objects, searching for background galaxies, for background QSOs. We have one group in Cordoba who's looking for galaxy clusters behind the Milky Way. There's a group working on the Sagittarius dwarf, and many more topics. Some were included in the proposal, some were not, because they just appeared because the data were just so amazing and allow us to do other things as well. Observing strategy is the same for VVV and VVVX. It's a multi-epoch survey. Depending on the area, we have between 24 epochs in the K-band and 310. Those numbers refer to observations that were accepted by the quality control from ESO after the observing. So the numbers might slightly change depending on whether that includes our own quality control or whether it is the data that were reduced by CASU, because CASU is, I think, reducing all of the available data, even if the quality is not 100% within requirements. Okay, we do, for VVV, we have 5 broadband filters, Y, Z, J, H, and K. Unfortunately, for VVVX, there was not enough time to include Y and Z again. So we have to live with only the JH and K filter. Wide field survey, yeah, we do about 1,700 square degrees. And because of the extension, we now connect to the UKITS Galactic Plane Survey. And now with VVVX, we also cover those gaps. The green fields is VHS, purple is us, and now extending to 4.5 degrees. We have a few gaps here where you see the triangles, but we are now much closer and partly overlap. This is actually the original VVV. So these gaps are now mostly closed. We'll come back to that image in a while. Okay, it's a variability survey. We have short exposures, 2 seconds, 4-second exposures in KS, 6 seconds in H band, and 10 seconds in J. The one exception is the K band observation for the disk in the multicolor campaign. That was decided to be 6 seconds, but for the variability, they're all 4-second exposures. We try to avoid repeating observations within a short time scale because it's variability. That's mostly done by setting priorities. We had a few problems with that, but I will come back to that later as well. Short exposures means we can't use AAO because that requires a minimum time. We don't use guiding because short exposure is not really necessary. It's a 2-point dither, for same principle for all filters. As I said, unfortunately, no Y and Z in VVVX. In the infrared, the biggest problem is the sky subtraction. And before the survey started, CASU did some tests, how to combine, how many tiles need to be combined to allow for proper sky subtraction. That's why all our fields are combined in concatenations, depending where the field is, how crowded it is, between 4 and 8 tiles. The overlap between the tiles was set to 1 arc-minute, which comes in very handy again for the variability study, because if a tile is not observed in the same concatenation, that means we are adding epochs, because the same star is covered by different tiles, makes the light curve even more valuable. Okay. But since we needed concatenations and the observing tool doesn't allow the combination of containers, unfortunately, we couldn't set fixed cadence. So the light curves are not populated in a consistent way. The cadence is pretty random, fortunately. Yeah, from the beginning of the survey, we had a very good plan what was supposed to be done when, and that probably lasted for the first week of observing, and then the weather comes in and priorities of the other surveys. What you see here is actually how the observations were distributed for VVV and VVVX. The red areas is VVV, original bulge and the disk area. Dark blue is the upper disk and the lower disk. The yellow one is the extension to longitude 230 degrees. Bright blue is the upper and the lower bulge, and green is the disk extension to plus 20 degree longitude. So the very long blocks are usually ones where we did multicolor observations, especially the Y and Z, because they had the highest seeing constraints, and that took the longest to be completed. The gray area is time we were granted to repeat observations that were not within specifications and were graded D. So most of them actually we got time to repeat those observations. This is where the long time baseline comes from. At the end of 2022, beginning 2023, we got an additional 200 hours to do multi-epoch observations again for the bulge. Okay, yeah, I usually do the completeness plot saying how many observations were done. I'm not really sure. It's probably hard to see. In the inner disk bulge area, we have fields with up to 300 epochs. The bright blue areas have 24, 26. If you include the gray D repeat observations, the same goes for the disk 20 area. The original disk here has about 50 to 60 epochs. Yellow was decided we try for 38, 39. And the lower disk and upper disk also have 24, 26 epochs in KS band. For the multicolor observations, we have 2 runs in JH and K for the VVV, for the largest fraction of the bulge in the VVV and the disk. The inner disk area here has actually up to 6 JH and K observations because we wanted to have deeper data. Okay, for the VVVX area, we did JH and K only once, but with multiple exposures to also have deeper data available. But they were distributed differently because we needed the concatenations, but there's also the 1 hour, 5 minute time limit for containers. So we had to split the J band over 2 observing blocks. I said we only got Y and Z once for the VVV. We also got 20 extra hours to work because CASU decided they wanted to check the calibration in Z and Y in the most reddened areas. So we submitted 20 hours of OBs to observe the innermost region in Y and Z and sandwich that between fields that are farther away from the most reddened areas to check the calibration for the inner disk, for the galactic plane in those 2 filters. But they were only done for 1 row of tiles. Okay. So this is the distribution of the cadence for each of the areas. We have a few fields, 8 tiles where we have the 310 epochs. They are sitting in the Bardis window because where we have also optical data from the Ogle survey. So it was decided we use that to have a much higher number of epochs. These are 42 tiles in the galactic plane where we got the 200 extra hours at the end of the survey. So they are up to 150 epochs now for those fields. These 2 blips are data we got including the science verification. So they were overlapping with that, so they have a few more epochs. They should all have the same number of epochs, but as I said, we got grade D repetitions, and so there is slight variability and of course gaps because we can't observe And I think we all know what these gaps are. That's pandemic hitting us badly. Same thing for the other three fields. We had a few concatenations where unfortunately the fields were observed 5 times in one night, one after another. So, but they were recovered in the grade D observation. So these were unfortunately also fields that only got 24 epochs to begin with, and doing 5 in one night didn't help with the time baseline. But we got the time to repeat 3 of those observations to recover a number of epochs. So I don't really work with variability data. So my connection comes mostly, I've been doing or started a completeness test to see how many of the stars or how deep are the data, how many of our target stars are we actually missing. And that also goes back to the fact that we have different numbers of epochs for each of our target stars, depending on brightness, not only because we have a random cadence, but also because for the surveys, our observing constraints changed. So in general, you could say half the epochs were supposed to be with seeing 1 arcsecond and better. And for the second half of the epochs, there were no seeing constraints, which in ESO terms for the phase 2 tool means 2 arcsecond seeing. There are very few observations where the seeing really got that bad. And the seeing was the only condition that wasn't fulfilled. Usually there are other problems as well with the weather. But we have some observations with 1.7 arcsecond seeing. And so I wanted to see how many of the stars are we missing. In 2012, Istvan Dekeny started a project where he tried to estimate how many epochs do we need if we assume random cadence for the light curves to detect a certain type of variable star. The red and blue are 2 different types of variable stars. So this is an example, depending on the KS magnitude, how's the cumulated detection efficiency if we assume 40 randomly distributed epochs. Okay. So, which means up to 15 magnitude, we're actually doing pretty good. 14 epochs is what is fulfilled pretty much for the inner disk and for the bulge area. Okay. So just as a comparison, actually the efficiency drops down very quickly. This is for 20 epochs. So we have a little bit more for the lower bulge and the upper bulge, but we are still going to miss quite a large fraction of the variable stars. 40 to 80 would be much more efficient. So I tried to run the completeness test with that in mind. At the moment, I'm running the completeness test for the Casu photometry using their pipeline you can download, and decided I go for the detector 5 images under best seeing, lowest air mass, and lowest ellipticity. So the plots you see here, unfortunately a little weak, is the seeing distribution, the best seeing distribution for all the tiles in the survey. This is disk, bulge, high and low bulge. The green and the blue is the 2 different regions. The red one is the sum of both. This is disk 20, disk 230, and the lower and higher disk. So best seeing is between 0.4, 0.6 arcsecond, which is really good. I even found a few which is below 0.4. I didn't want to do the PSF for every single tile, so I grouped the different images into bins and used the PSF template for 0.4, 0.5, and 0.6 arcsecond seeing to add 500 artificial stars in a magnitude range 11 to 20.5. They are the same artificial stars or star positions for each of them, and it was set in a way that artificial stars are not overlapping with each other. So there's a position difference of 20 pixels between artificial stars. Yep. If you want to add or I created a PSF, which you need for add star in Dauerfort. You need the shape of the PSF, and I think if you want to be very accurate, you have to do this for every image because you are using that data set. Okay. So I wanted to speed up things a little bit, so I created a PSF for using an image with 0.4 arcsecond seeing and use that for the range 0.35 to 0.45. So I have a representative PSF, so it's not, it allows for small offset. Okay. No, it's from the image.
Sorry, okay.
No, it's from the image. So you use
an empirical PSF created with Dauerfort. It's not simulated.
No.
Okay. Thank you. Sorry.
Okay, so as I said, for the whole area, I used the best seeing, but I wanted to show you a comparison for the worst seeing, which is on the top, and how it changes for the best seeing. These are 3 different fields. 261 is in the bulge area, but, it's in the bulge area. I need to speed up, but not very extinct. Tile 333 is the tile that covers the galactic center, so very crowded, high extinction. And 404 is in the lower bulge at -15 degrees, where we assume it's the lowest reddening and the lowest density. It's not exactly crowding problem. The blue and the red curves are 2 different definitions of completeness, in a sense. Blue means I'm just checking, is the star recovered or not? So no other constraint. Whereas for the red curves, I also request that the recovered magnitude has to be within 0.5 magnitude of the input magnitude. It's just something I found in papers from HST Galactic or Globular Cluster Survey. They use a 0.75 magnitude offset as a limit. I decided I go a little bit lower. We are pretty, for the less crowded areas, you see we are pretty good doing up to 16.5. It drops very quickly, and here for the very good seeing, you also see where the saturation hits us. The recovered magnitude is off quite a bit. Again, this is all aperture photometry from CASU, and I think Javier will include a little bit using Dufort PSF photometry, and he will show you there is actually some change, significant change actually in some cases. Yeah, so these are the plots, and that's where the link with the different science topics from the survey comes from. This is a contour plot for the best seeing completeness for a 12.5 magnitude star, and this is for 15th magnitude star in the bulge area. So here would be tile 201, and this is tile 396. Okay. How does that connect? The image you see here is one of the first globular clusters we found in the survey. Was published in 2019. Dante found it. This is VVVCL001. Okay, in the first data set, unfortunately, wasn't deep enough to reach the main sequence turnoff, so we didn't. The estimates of the distance was not as good as we were hoping, because if this cluster is at the same distance as UKS1, that would have meant there is a chance that this is a binary cluster, which there are not that many known, or they are not known in the Milky Way. Would have been interesting to find one, but it turns out that's not the case. But with later data, especially spectroscopic data, it was found that this is a very interesting cluster nonetheless, because it's one of the most metal poor, metallicity at -2.4 something in the inner galaxy. Okay, but if you look at the completeness, here it drops really off, so we still don't really have the lower area. Maybe worth checking if you combine a few of the best seeing observations to reach deeper. This is for the variability. This is again the same plot you show at the one of the first slides, a work by Philippe Grand, looking for our Lyrae stars down here. This is where tile 201 is. Most of them are exactly in that range, 50 magnitude, plus minus, where at least in that tile we are in the range of 90% complete. So we're not missing much there. Fortunately, that's going to change. Javier is going to talk as well about variables in globular clusters. This is actually borrowed from his work. These are the variables found in NGC 6441, and if I remember correctly, that's somewhere here, -5 degrees. Okay, so you find, again, in the range where I show the completeness here, not only the purple objects are the Lyraes, we find eclipsed binaries. The really bright one is Cepheids. The triangulars are unclassified areas, unclassified stars, sorry. And the cyan circles are objects that had to be rejected as cluster members after all. I need to speed up. There's a microlensing group, is Gabriela Navarro. She works in Italy, and she actually used the data to look for latitude dependencies for microlensing events. Okay, so the plot you see here are the color-coded areas are different tiles along that line. These are the microlensing events where unfortunately we only have the K-band and no color information. These are the microlensing events where we actually do, unfortunately. So this central region here, they should be red. These are the red clump stars. The black symbols are other microlensing events. It's just nice to, I just wanted to see how also these events compare to our completeness and how much we might miss because of our completeness issues, I think. One of the earliest works was by Roberto Saito. He started a project for doing demographics because it's a wide field survey. We can look for systematics or take real advantage of the wide area of our survey. This was done on the bulge, checking for the different structures from the CMDs depending on position. We have a group, this is completeness for the disk. We have a group that looks for background galaxies. It's actually a very extensive work by Laura Baravalle. We even found a new, until now unknown galaxy cluster in the data. Okay. They also developed a pipeline which helps classifying those background objects and have a very high rate of confirmation. By the way, I have to admit, it's very astonishing. They check every single image they find that has been confirmed by eye as well. So in some areas, they check 5,000 images to look whether there is really a background galaxy. We look for clusters. This is one of the clusters Dante found, was published in 2017. That's the cluster, has metallicity estimates based on metallicity estimates. We have distance estimates using the Lyraes and RGBs stars, and was found -1.4 dex metallicity and is roughly at a distance of I think 7 to 8 kiloparsecs. Yeah, this is a comparison between the photometric completeness between aperture and PSF photometry was done by Javier. In general, as expected on the faint and the PSF photometry is doing better, much better. But for the very bright ones, Casio pipeline can handle saturated stars a little bit better. So that's where there's a slight advantage for the PSF photometry. But in general, looks like I have to repeat the completeness test doing the PSF. In the disk, we also have Jura Borisova is searching for star clusters, and we found hundreds of them. They are also all visually inspected afterward. And yeah, for some, we even have rough age estimates. Okay. This is another work done for the background galaxies. This is in the disk 220 area, where they also found among 700,000 extragalactic candidates, and found 5,000 that were all visually inspected. So this is a lot. This is a stellar, the reddish color is actually a stellar density. Then the white objects are the background galaxies. Sagittarius dwarf galaxy in the lower bulge area. That is where Dante has been searching for new globular clusters. It's a plot you see here. Again, everything up to 16.5, 17. We are about 50% complete. So, but we are still missing. We might be missing a lot in a sense. Okay. And bulge high, unfortunately, I only found one paper so far. That's also a search for globular clusters by Bika et al. From 2018, where we are just deep enough, or we are not really deep enough to get the complete main sequence turnoff. Makes it a little bit difficult with the distance, but coding images might help. In the lower disk, we had a student at UNAP who uses combination of Gaia and VVVX data also to look for new clusters. That's one of the examples. This is from the Gaia image. This is the Sarsenius galaxy, where, by the way, we also have a former student working on searching for globular clusters. This is a zoom in, and this is a stellar density from the VVVX data. One work that actually includes now the whole DIS 220 area. Again, this is searching for background galaxies by Sol Alonso. She's from San Juan in Argentina, and she's leading that work on the Southern Galactic Disk. Unfortunately, I don't have the completeness plot for the DIS 220 area. It takes a little bit longer than I anticipated. But before I stop now, the VVV and the VVVX survey have been very successful by doing science data, but it actually turns out also in the data reduction there has been a lot of work done. So as I said, I used CASU so far, but PSF photometry using DOFOT or DAOFOT by the Schizo pipeline. That's the third one. There are also some independent data pipelines. One I found by Lepralato. Unfortunately, I didn't have a name in the paper, but I also found a few months ago in AstroPH WordCamp pipe, which I'm very happy to see that Stefan Meingast, he's going to give a talk later, and I really hope he includes that in his presentation. Would be very interested to see how that changes things. And one last example is, in case you're into data reduction, the FELI pipeline is now also including WordCamp data. Although you really have to start from scratch, so you need a lot of data value. I'm just taking advantage of other people's work here, so my conclusion is actually just this stunning picture ESO produced for the bulge area. I don't know if you remember a few years ago where you could zoom in and spend hours of looking at them in the Milky Way. Thank you.